Okay, so I remembered to record today. My video is working, so that's good. Okay, so as I have written down here yesterday, we talked about manifolds, definitions and examples. And so the examples, we showed that open subsets of Euclidean space are manifolds in an obvious way. And then we showed at some length that S1, this unit circle in R2, is a manifold, and we did that by constructing an atlas for it. Okay, so today we'll certainly talk about submanifolds, and then time permitting, we'll talk about mappings between manifolds. Okay, this is sort of carrying on a process that you typically do when you introduce a new kind of mathematical object, in this case manifolds, is that you talk about sub-objects. So sub-manifolds. So for vector spaces, you have subspaces. For groups, you have subgroups, and so on. And the other thing you do when you introduce a new kind of object is typically you talk about mappings between two objects of that kind. So for vector spaces, those are linear mappings, and so for groups, those are homomorphisms of groups. And so in this case, we're going to have the notion of a mapping between manifolds, and we may get to that today, or we may not. I don't know. Okay, but submanifolds. All right, so I'll just give the definition, and corresponding to the definition will be a picture, which I'll get to shortly. But first, the definition. Oh, so sorry, one thing I'll just say, I won't, nothing needs to be written down about this. Well, actually, I take that back. Let me write something down, just so I did. So typically when we talk about manifolds, we talk about their dimension. So a manifold has dimension n, and n of course is a non-negative integer. Dimension could be 0. It's the same as a vector space could have 0 dimension. So a manifold has dimension n if it has an atlas all of whose charts take values in, so I'm defining dimension, in Rn, where that n is being specified. Okay, so there's no reason that a manifold even has to have a well-defined dimension, unlike a vector space, which always has a well-defined dimension, even if it's infinite dimensional. A manifold does not necessarily have to have a well-defined dimension. Okay, all right, so, but we'll almost exclusively be dealing with manifolds which do have a well-defined dimension, but you should know that that may not be the case. All right. So a submanifold of, so a submanifold S of a manifold M. Okay, so remember that a manifold is a set with an equivalence class of atlases. And typically you define an equivalence class of atlases by choosing one atlas, right? So that's what we did yesterday. So a submanifold S of a manifold M is a subset with the property of that okay, so for each x in S, okay, there exists a chart U phi for M. Okay, so that means it's one of the charts which is sort of compatible with your atlas, such that, okay, two properties hold. All right, so the first property is that phi maps U into, so we know the charts map into Euclidean space. We're going to take our Euclidean space and we're going to, which is Rn, and we're going to write it as a product. Rk cross Rn minus k. And of course, this is really just Rn, but all I'm doing is explicitly recognizing the fact that that Rn can be written as a product of Rk and Rn minus k. So that's really not saying anything. The meat of the definition is the second part, is that phi of S intersect U sits inside Rk cross 0. Right, and so when you restrict this chart to 2 points in S, in this product, it only takes values in the first component. All right. So there's a, as I said, there's a simple picture associated with this, which I will draw. Okay, so here's our typical manifold. Okay, so this is our manifold M, and a submanifold, and so we think of a in this picture we intuitively imagine a manifold to be this kind of a surface, and a submanifold is some nice looking thing like this, and so the definition says that if you take any point X in, so this will be our supposed submanifold S, and so for any X in S, you take a chart, okay, U about X, okay, and here's our map phi, and this maps into Rn, but Rn we write as a product of Rk and Rn minus k, like so. And the definition says that this chart should have the property that the points here in S get mapped to the Rk part of this product. All right. So so that looks like this. Okay, and so this bit right here, all right, so this is phi of U, and this bit right here is phi of S intersect U. Okay, so that's how to picture what that definition means. So let's look at a simple example. Okay, so the example we'll look at is the circle that we talked about last time. And so last time we saw that the circle was a manifold. And so what we're now going to show is that it's a submanifold of R2. So we're going to show that S1 is a submanifold of R2. Okay. And so what I need to do, according to my definition, okay, so here's S1 sitting inside R2, so X, Y, okay, is I need to find for every point on the circle, I have to find a chart which has the properties depicted in this picture here. Okay. All right, so I'm going to choose any point on the circle except this one. Okay, and this one you'll have to do a different construction than the one I'm about to give, but it follows in a similarly obvious way. So I need to find a chart now. So remember, the chart here is not a chart for S1. it's a chart for R2 that we have to find. And we have to find a chart for R2, which maps the circle into, one component of R2, all right? Now, if you think about it, there's a pretty obvious set of coordinates for R2 that you're going to choose. So for example, the normal Cartesian coordinates for R2, X and Y, those are not going to work, right? Because according to this picture here, one of the coordinate functions has to be constant, right? And certainly X and Y are, neither of X and Y are constant around a circle, right? So we have to choose a coordinate chart for R2, which has the property that one of its coordinate functions is constant along the circle, and by just shifting, we can make that constant equal to 0. So what coordinates can you think of for the plane which will have a property like that? This is a place where you can chip in.
Is polar coordinate?
Yeah, polar coordinates, okay. So let's define polar coordinates. We haven't actually done that yet. So we need to do that carefully in this kind of world where you choose charts and a chart U and a chart map phi, okay. So the polar coordinates we're going to choose to be valid on a domain which excludes that little chunk of the plane here. Okay, so we're going to excise that bit and we're going to use polar coordinates on the rest. Okay, so use polar coordinates. Okay, so I'm going to be consistent. So normally you think of polar coordinates as being r theta, right? But if we're going to sort of, verbatim duplicate this picture, we can't quite use r because along the circle, r is equal to 1. And so, really we have to, subtract 1 off, but let's just sort of see how that goes. So it's not quite polar coordinates, it's a simple sort of elementary adaptation of polar coordinates, okay? So we take U to be set of points X and Y. So remember the U is going to be a chart for R2. Okay, so we're going to take, R2. And we're going to eliminate the points of the form, here, let me write that in a different way. That's a little easier for me to write down. So we're going to take R2 and we're going to excise the following set of points. We're going to take the points, take away the points X0, where X is less than or equal to 0, like that. Okay, so that's just like I did in the picture here. It's removing that bit. Okay, and then I need to choose my chart map phi. And so phi is going to take values in R2. And so according to this picture here, we're going to define sort of R and theta. And according to this picture here, so we know that R along the circle has the value 1. And so we need for the value to not be 1, but to be 0 corresponding to this. So our coordinates actually aren't going to be R and theta. They're going to be theta and R minus 1. Is the point, okay? Sorry. So I'm going to take a point. Okay, so I said that it's going to be theta and R minus 1. So theta is, as we saw yesterday when we put charts on S1, we had this atan function. So that's going to be theta. And then we go square root of x squared plus y squared minus 1. Okay, and so again, the minus 1 is to shift the radius from being 1 along the circle to being 0, because 0 is what's required in that picture. Okay. All right. So in this case, okay, so let's look at what that chart does. Okay, so here's R2, here's S1. And now I'm mapping into, and so I'm going to call this coordinate R, sorry, theta, and I'm going to call this coordinate R. And so I know that my chart map phi is going to map into R2. Okay, and R2, so this has, this is the normal R2, which has coordinates X and Y. And then we're going to be mapping into some version of R2, which is parameterized by theta and R. Okay, so our U, again, our U looks like R2, take away that point. Okay, so U kind of looks like this. Okay, now what's the, when I take this U and I map it into R2 parameterized by theta and R, what's this going to look like? Okay, so what are the values of R and theta that are taken by phi? Okay, so I know that theta goes from minus pi to pi. Okay, so in this picture here, I should go minus pi to pi. All right, and then R is obviously going to be the way I've drawn it here. Sorry, the way I've defined R. Remember, I'm shifting by -1, and so R is actually going to go down to -1. And so the image of phi looks like this. It's that bit in there. Okay. And moreover, if I take U and I intersect it with S1, which is my submanifold S, U intersect S is this set here. Okay, so that is U intersect S. And then when I take its image here, it gets mapped to that little bit there. Okay, and so I'm exactly in the picture that I drew up here. Okay, and so this shows so thus S1 is a submanifold of R2. Okay, any questions about that? All right, so very often, so first let me maybe say some things about, well, one thing about submanifolds first. So it's easy to show the following fact. Submanifolds are manifolds. Okay, now I'm not going to prove that. It's elementary in some sense from the definition. So let's just go to the definition and kind of see why that's true. What do you have to do to prove that something is a manifold? You have to build an atlas for it. Well, obviously the way you're going to build an atlas is exactly suggested by the definition. Around every point, you're going to take an original chart for M, okay, which is this thing. Okay, and has this property. But then if I take, so my submanifold, the chart for the submanifold is simply going to be U intersect S. Okay, and instead of mapping it into Rn, Rk cross Rn minus k, I'm just going to map it into Rk, and that's going to define my submanifold chart, just sort of restricting phi to this intersection. And the definition is contrived so that that gives me a chart which takes values in Rk. Right? And you can do that about every point in S by definition. And so, so that's how you build an atlas for a submanifold. Okay, you know, you have to verify some stuff there, but it's fairly straightforward. Okay. Now, you typically do not build submanifolds by verifying this property. Okay, that's not often the way you do it, although that's how we did it in this example. A common way of building submanifolds is by using what's called the implicit function theorem. Okay, so the implicit function theorem sometimes is something that gets taught in 280, but normally it doesn't. So I'm not going to assume that we know what it is. So it's a simple enough thing to write down. Okay. Okay, here's what it says. It says let U in Rn be an open set and let F from U into Rm be infinitely differentiable. Okay, so that's the starting point. And so what I want to do is I want to take a subset of Rm, okay, and then I'm going to consider all points in U which map to that subset in Rm, and I'm going to give conditions on F under which the subset of U which maps to that given subset of Rm is a submanifold. Okay, that's the idea. Okay, so let R, so maybe I shouldn't call it R because it looks too much like Rn. So let A be in Rk have the property that, okay, so it's going to have the property that for every Y in A and every X in the preimage, so my experience is that preimage sometimes isn't familiar to you, so let me write it down explicitly. So for every X in the preimage of Y under F, okay, and so that's F inverse. That doesn't mean that F is invertible. This is preimage, and the preimage is by definition is the following thing. So it's the set of all X primes in U such that F of X prime is equal to Y. Okay, so that's what the preimage of Y is. So that for every Y in A and every X in the preimage of Y, the derivative of phi, the derivative of F at X has rank. Let me say it differently, is onto. Okay, so that means, so the derivative, remember, so this is just the normal Jacobian, right? So you take F, you calculate its Jacobian, you evaluate that at the point X. That's going to be just some linear map. So let me make that clear that that's a linear map. So that's going to be a matrix. So and what's the shape of that matrix going to be? Well, F is a map from Rn, essentially, use an open subset of Rn, into Rm. And so it's going to have M rows and N columns, okay? Okay, so that thing has to be onto, which means it should have full column rank, is another way to say that. Okay, so if that's true, so then what's true? Then F inverse of A, okay, so F inverse of A is the preimage of A, all right, so that is, by definition, the set of X's in U, so that F of X is in A. So we'll see how to use this theorem in a second. Okay, then this thing is a submanifold of U. Okay, so that's the implicit function theorem. So let's take a look at how we can use the implicit function theorem to build manifolds in a simple way. Okay, so let's prove that the n-dimensional sphere, so remember what the n-dimensional sphere is. The n-dimensional sphere is the set of all vectors in n+1 dimensional Euclidean space with norm 1. Okay, so I'm going to show that this is a submanifold of Rn plus 1. Okay, and I'm going to do that using the implicit function theorem. Okay, so the thing that I notice is that Sn is equal to the pre-image of the point 1 where F is the mapping from Rn plus 1 into R defined by, it takes X to the norm of X squared. Okay, I mean, that's just obvious, right? So this is just the definition of Sn, right? So Sn is the set of points X in Rn plus 1, which take the value 1 under this map F. That's just exactly the definition of Sn. Okay, but you notice that this sets me up now to use the implicit function theorem. Okay, so what I'm going to do is I'm going to take A to be the point 1 in R here, and then I'm going to verify that the hypotheses of the implicit function theorem hold, and that will give me the conclusions. All right. Okay. So to do that, I need to calculate okay. So notice that I can also write norm of X squared as the inner product. Right. And so this is the Euclidean inner product. Okay, so that's for the purposes of taking derivatives, that's a useful form of the norm of X squared, because I'm going to calculate now the derivative of F. Oops, I didn't need to do that. I'm going to calculate the derivative of F, where F is equal to that function. All right. Okay, so and so I'm going to calculate the derivative of, please go away, df at the point x, and I'm going to calculate the derivative in the direction of a vector v in Rn. Okay, so I'm going to take some vector v, so I'm calculating the directional derivative of f at x in the direction of v. Okay. And the reason that this form of the function is maybe easier for the purposes of calculating derivatives is I see that it's a quadratic function. And so to differentiate it, I can fix one of the arguments and take the derivative with respect to the other one. And then I can fix the other argument and take the derivatives with respect to that one. Okay, so if I do that, and taking derivatives in the direction of v, what I get is, all right, so I fix the first argument, let's say, and differentiate with respect to the second argument in the direction of v. And if you think about that for a second, what you get is this. And then if you fix the second argument and differentiate the first argument in the direction of v, you get that. Okay. And because the inner product is symmetric, this is simply 2xv. All right, so that's the derivative. You can, if I went too fast calculating that derivative, you can write this out explicitly, right? It's just the sum of the components squared, and you could just directly and explicitly calculate it using that formula. But this is what you'll get. Okay. All right, so that's the derivative. Good. Now what I need to verify is I need to verify, according to the implicit function theorem, that this derivative is onto at every point x, which is in the pre-image of A. Okay. All right, so let x be in and here I'm going to take A to simply be the set 1. Okay, because of this fact. All right. Okay. Okay. So what I need to show is I need to show that the derivative, as I've calculated it here, is onto. Well, the derivative here. So note that df at x is a linear map from Rn plus 1 into R1, okay? Just because f is a map from Rn plus 1 into R1, so the derivative will be a linear map between those same two spaces, okay? And so now if you have a linear map which takes values in a one-dimensional vector space like this, there's a very simple rule for when that linear map is onto. What do you think that might be? What's the only example of a linear map into a one-dimensional vector space which is not onto? There's only one linear map which isn't onto. What is that linear map?
The zero map.
Yeah, the zero map, exactly. Okay, so to verify that this thing is onto, all I need to show is that it's not zero. All right. That's right. So it's thus onto if and only if, sorry, I'm writing a little f instead of big F, sorry. Okay. All right, so I need to just verify that for every point x in the pre-image of 1, that that this thing is not 0. And so why is it not 0? Okay, but this is true. All right, so let me ask you another question. If this is your linear map, okay, so your linear map is the map which sends V into that, okay? When will this linear map be non-zero? So the linear map is just the map which fixes an x and takes the inner product of x with v and multiplies it by 2, but the 2 doesn't matter. When will that linear map be 0? What property should x have in order for that linear map to be 0? In other words, what property should x have in order that every vector in Rn plus 1 be orthogonal to x? What's the only vector which is orthogonal to every vector?
the zero vector.
Exactly. Okay. And so this is true since x is not equal to 0. Okay. So in other words, the hypotheses of the implicit function theorem hold. And so the conclusions of the implicit function theorem are that Sn, which is the preimage of 1, is a submanifold. Okay. So that's so we showed, and so therefore by my fact here, this also shows that Sn is a manifold. Okay, and last time we showed explicitly that S1 is a manifold, but this shows us that Sn is a manifold for every n, and it does it in a slicker sort of a way. We don't have to calculate explicitly an atlas in this case. Okay, let's look at another example. Okay, so we had On. So remember that On was the set of n by n matrices, which are orthogonal. Okay, now we don't really know what that set looks like. Okay, it's kind of a complicated thing. But we can nevertheless show that it's a manifold, and we'll do this using the implicit function theorem. Okay, and to do that, we're going to use the definition of On, because just like the n-dimensional sphere is defined by asking that some function takes certain values on Sn. On is defined by a certain function, namely the function R transpose, should take some values on On, namely the value equal to the identity matrix. Okay, so let's define f from Rn by n, into, okay, so the function is going to be the function which takes a matrix and multiplies it by its transpose, right? So if you take a matrix and multiply it by a transpose, well, the result is certainly an n by n matrix, but it's an n by n matrix which is very particular, namely it's symmetric, right? If you go, so this matrix is symmetric. If you take its transpose, you get itself back again. Okay, so we're not going to take functions which take values in Rn by n. We're going to take functions which take values in the set of symmetric n by n matrices. Okay. All right. So, and this function, and I'm going to take now an arbitrary n by n matrix. So I'm not going to write it as R because R suggests that it's an orthogonal matrix. So, yeah, an orthogonal matrix. I'm going to take an arbitrary n by n matrix A, and the function then is obviously going to be A transpose. Okay. And then we note that On is the preimage of the identity matrix under this mapping F. Right? That again, that's just the definition of ON. Okay, so to show that ON is a submanifold, I will apply the implicit function theorem. Okay, so this means I have to show that the derivative of this thing F is onto at every point which is in the pre-image. All right. Okay, so let's calculate. So we need to calculate some stuff now. So let's calculate the derivative. And I'm going to do just like I did in the example up here. I calculated the derivative of F at X in the direction of V. Here I'm going to calculate the derivative of F at A in the direction of some other matrix or some other vector in my vector space, which is the vector space of matrices here. Okay. Okay, so I go df at A. Okay, so the derivative of F at A in the direction of B. Okay. And again, I notice here that this function F is quadratic. And so you can differentiate F by fixing the first argument and differentiating with respect to the second, or fixing the second argument and differentiating with respect to the first. Okay, and then use the product rule. Right. So I'm first going to fix the first entry and differentiate with respect to the second. So I'm going to differentiate with respect to A here, and I'm going to differentiate in the direction of B. And if you do that, you get A, B transpose. Okay. Then I'm going to differentiate with respect to the first argument, leaving the second argument fixed, and that gets me B, A transpose. Okay, so that's the derivative of my function F in the at A in the direction of B. All right. Okay, now for R in F inverse of the identity, we need to show that df at R is onto. Okay, because again, that's what the implicit function theorem needs, right? So you take an A, and an A in this case is just going to be the set, the singleton identity matrix. So you take every point in A and every X in the pre-image of that point, you need to show that the derivative is onto. Okay, so here we're going to directly show that it's onto by taking a vector in the codomain of this linear map. Okay, and so the codomain of this linear map is the set of symmetric n by n matrices, and I'm going to show that there's some B which maps onto that. Okay. Okay, so we need to show that that thing is onto. So indeed, given S, so S is going to be a symmetric n by n matrix. I'm going to take B to be equal to 1/2, I think it's RS. Okay. Sorry, I'm going to, because if I get that wrong, it's just going to make a big mess. So let me make sure I got the order right and I got the transposes right. Oh, I got it backwards. So I'm glad I checked. Okay, so this should be, let me just double check. So it should be SR. Okay, good, sorry. Okay, and so what I'm going to show is that if I take now the derivative of f at r, okay, and evaluate it in the direction of b, that I get s back, and that will show that it's onto. Okay, so then df at r evaluated at 1/2 SR. So hopefully I did my calculations right. Okay, so this is R. Okay, so there's going to be a half there. Okay, so it's going to be R, and then it's B transpose, but B is equal to, 1/2 SR. So I'm going to take the transpose of that. So that's going to be R transpose S transpose. And then I'm going to calculate this one now with B equal to 1/2 SR. So it's going to be 1/2 SR, and A is equal to R. So this is R transpose. Okay, and so then you notice that R is in the pre-image of the identity. Okay, which means that R transpose is equal to the identity. So both of these are equal to the identity. And because S is symmetric, this is equal to S. Okay, so therefore I've shown that given any symmetric S, there's a B for which the derivative of f at R in the direction of this B gives me S. So that's exactly showing that the derivative is onto. Okay, and this shows that by the implicit function theorem, ON is a submanifold. Okay. All right. And then because SON is equal to ON, R in ON, so that the determinant of R is equal to 1, okay, as opposed to the other possibility, which is -1. Okay, so there's some stuff here that you have to spend some time thinking about to see why this is itself a manifold. Okay, and so why is that? So again, it amounts to really the possibility that in ON, a determinant can either be +1 or -1. And so what this means is that ON is a union of two things, right? It's a union of all the R's in ON with the determinant 1, and it's all the R's in ON with the determinant -1, okay? And those two things are obviously disjoint. Can't have determinant 1 and determinant -1 at the same time. And I've already shown that ON is a submanifold. And so I have these two kind of disjoint bits of ON, okay? And if ON is a submanifold, then each of the disjoint bits also has to be a submanifold. That's kind of the argument there, okay? And I will summarize that by just saying that okay. All right, so so that's nice because as we've seen, ON and SON are important to us because they arise as the set of configurations, the set of rotations of a rigid body fixed at a point. Okay. All right, so I think that does me for today. Any questions about all of that? Okay, well, I will stop the recording and I'll stick around for a second if anybody has any questions.